Hey everyone. Sorry, my name is Charl. You introduced me. Let me just go to the next slide. There we go. Okay, cool. So yeah, like I mentioned, my name is Charl. I'm from Kosher Consult, and today I will be speaking about uncovering new possibilities in engineering using high performance computing. Now the key, sorry, just want to check. Okay, cool. I just have the laser there. So the key talking points for today is I will just be giving some background on my company, what we do. That will be kind of short. Then I'll be kind of asking the question and answering the question, why do we use high performance computing? And then I'll be presenting to you guys 3 CFD projects that we did currently to kind of demonstrate the value you get from using high performance computing and also the value that the clients get from these kind of CFD simulations. And then lastly, we'll end off with some conclusions. So at Kosher Consult, we are a team of engineers who do fit for purpose solutions to contemporary business challenges. And we do that by strategically integrating emerging and maturing technologies into engineering projects and business process workflows. And one thing I think we all can agree on is that time is valuable. Time, in essence, is money. So we focus on streamlining your workflows and focusing your time on what it matters most to you, your business and your clients. Sorry, just going on back there. So at Kosher Consult, we have 3 distinct services that we utilize to kind of bring that unique value and insight into everything we do. So firstly, we have computer-aided engineering, which is obviously more specifically for today's discussion. And then we have digital engineering as well. And lastly, engineering consulting. Now, more specifically, more focusing on the computer engineering side of things, the services that are included in our computer engineering services are CAD designs, computational fluid dynamics, finite element analysis, and quite a recent, well, not quite recent, but it's a very coming more popular and a very intense computationally expensive kind of problem, fluid structure interactions as well. So just to give an idea of kind of the industries that we as a company have seen the experience in. So we have done work in the aerospace and defense, automotive and transportation, the fire safety and smoke ventilation, which is increasingly actually, which is interesting is that they are actually these days it's becoming kind of a compulsory thing to do kind of CFDs in these kind of situations and developments. Also HVAC and thermal comfort, marine and naval, then also natural convection, natural and mechanical ventilation, oil and gas, plant and mining industry, pharmaceutical also quite interesting with clean rooms, for example. And then pollution control, also quite popular one. Power generation, and the last 2 we have renewable energy and non-renewable, and lastly we have turbo machinery. And just for interest sake, these are all CFD projects or work that we've done in our company. The animation is playing here just to kind of display some of the capabilities and things that we are capable of doing within our company. Now, coming to the question, why do we actually now use high performance computing? Now, somebody actually, I think, mentioned it at this conference. I can't remember specifically who, but clients wanted the answers yesterday. Everybody's always like, as soon as possible. And the high performance computing makes that a reality, makes it possible to us to give clients results as soon as they can need it or even sometimes faster. Furthermore, we at Kosher Consult utilize the CHPC predominantly for all our HPC requirements. And with CHPC's affordable rates, we can do work at much more at competitive prices without actually increasing it to the extent that the client can't afford it. Furthermore, simulations today are getting more complex in physics. Like they want to include more detail, and that requires more computational power. Furthermore, the measures get larger and finer, and sometimes you have to capture even more geometric detail than before. And lastly, a great thing, for example, with the CHPC is with simulations, specifically what I do a lot, is that the requirement for storage. To run that simulation requires a lot of space, and the CHPC, for example, provides that space that we need to run our simulations without any trouble or hindrances. So now we get kind of to more the fun part, I think, just speaking about some of the CFD projects that we've done. So the first one, we did it for Lumax Energy, which is in the solar industry, and they wanted us to determine the wind load reduction factors for a very large solar array field. And they used this information, the forces, these reduction factors in the end to actually optimize their structures to actually save money and actually making it as needed a fit for purpose solution. So in the CFD model, we simulated incompressible flow, steady state simulation with fully turbulent. The wind speed we simulated was 36 meters per second. We simulated up to 40 rows, which is, to be honest, quite a lot. And we did 8 scenarios, 8 simulations. And the mesh size that we were looking at was around 55 to 68 million cells. Now, to tell you that to solve all of that in 8 simulations is quite computational expense, and the time required, even to do it locally, would take very long. So we used the CHPC and solved on typically on 240 cores, and we in the end were capable and able to deliver this CFD project, which initially would have taken 11 and a half days, 6 days. Just as an interesting result from the simulation, here below, what you can see is this is a side view of the flow approaching from the left-hand side at 36 meters per second. The first row of the solar panels is located here. And the rest of the 40, would all of them are basically located in this dark blue region at the bottom, in the wake of the first, basically, row, from the first, created by the first row. And I thought what always is so valuable is just to get some feedback from clients. And I just would like to maybe to highlight from what Salva and Roon from Lumax Energy just commented. They just saying like the results enabled us to optimize engineering structures with confidence. The next project I would like to highlight was quite a complex in terms of physics. So we were tasked to perform a verification of a Dropbox change design. And what this was all about, we did the end user was the mine. I was in the mining industry, Dundee Precious Metals. We worked together with Patterson and Cook and Delft on this project. And this whole Dropbox concept, what it comes down to is there's actually a hot gas with particles entering the system that needs to be removed from the system because they must basically minimize the amount of particles actually exiting through that outlet. So basically the idea was they usually drop out and fall on this floor, but then they usually have to take some time and open up the system to remove it. So now they want to remove it using a thin film of liquid or water actually flowing down here, transporting it into this trench and into the sump. But they needed to validate and verify that the system actually performs as intended and can actually do as required. So the CFD simulation, just in terms of physics, we simulated using the VOF simulation, VOF method, because there was obviously water and a gas. There was 2 different fluids within one system. There was also transient simulation. Therefore, also the requirements of a CHPC is obviously immensely important. And just to give an indication, we simulated 3 scenarios, but typically the mesh size was around 8.7. And this was mainly due to the fact that we had this very fine grating that we needed to capture, and to capture how the flow actually goes through there, because the region of interest is the trench. So you must make sure whatever goes on there, you're capturing sufficiently to actually answer the question of the project. Now, the wonderful thing is with the CHPC, we solved on roughly 120 cores, and we completed this project instead of 13 and a half days in 10 days. I think the next slide just shows a bit more of the results. So on the left-hand side, we can see the actual flow field of the off gas, of the hot gas coming into the system and actually exiting through that outlet. And this side, you can nicely see that water or slurry flowing down the slope into the sump, into the trench, and finally into the sump. Later on, the client actually came back to us for more. They wanted to actually analyze the particles as well. They also part of it, the design of the trench had to change a bit due to some construction constraints, and they wanted to confirm that it's still sufficient. And we included the particles in the simulation to kind of give them a good idea of what they can expect of where is it being transported, where is it settling. And what was wonderful is Patterson and Cook, a lot of the experiments that they did and our results correlated very well with what they had. And specifically with the particles, the client could say everything they saw in our simulations corresponded to what they know happens inside their Dropbox. And just quickly, some feedback just to kind of highlight, especially again, I think with the CHPC in mind, from Delft, they said we went the extra mile providing professional assessments and reports on time within a tight project line. This client actually came to us. Because they had a deadline of having to start constructing, and they only had certain times, as you would know in mines, there's certain shutdown, and you can't move them. If that's what it is, and you miss it, you're kind of in a sense in a bad position. So you're very strict on time. And lastly, I think just from Patterson and Cook, an international company as well, they just commented our technical experience and practical approach to slurry flow not only confirmed their laboratory test results, but also gave them in-depth understanding of the complex flow that they encountered, within the system. Then the final project, and this one, the first two, I just was more kind of an overview. The next one is one we actually did for EPCM. I think some of you might know them. They're a very large company also globally. So we did the simulation for them. Just to give some quick background, this big tank, as you can see the dimensions, 36 meters in diameter, roughly 25 meters high. It's a very big tank. The wall thicknesses range from 20 millimeters to around 8. And you can see the different colors represent the different thicknesses to show you, like you'll get thinner as you go to the top. And what they wanted here is they had what they call a heavy fuel oil that they basically needed to store and keep at a certain temperature to make it possible to pump it and actually transport it out of the system and to other places. And this oil is very, very viscous. It's almost like Marmite black, if you can imagine it like that. So 30 degrees Celsius is already too low. Then you can't work with it anymore. So they designed this heating solution that they practically just needed verification of. And we, just to give an indication, so what we did, the whole system was symmetrical, so we could half the model. And there in the corner there, we have this part. So we basically here, the HFO is being extracted and heated up and pumped back into the system via this one at around 60 degrees back into the system. And yeah, so with that, what we did, the first scenario that I wanted to simulate was a transit simulation of actually the HFO being continuously recycled, meaning reheated, for a 12-hour period for the worst case of heat loss to the environment. Now, just to say, many of you might, especially if you do CFD, would imagine simulating 12 hours. And just going back to the previous slide, do you know how small that hole is? Like how the mesh count and the size is so small, you'll see your current number and how that impacts your time step. And so simulating a problem like this for 12 hours was very computationally intense. And that's one of the biggest reasons why the CHPC was of highly value for us in this scenario. But just to say also, like we simulate just some modeling aspects, we did the transit simulation, like I mentioned, and because it's so highly viscous and the flow, and also looking at the Reynolds number and Rayleigh number, we could establish that both the air at the top and the HFO flow was both laminar. We again used the volume of fluid method to simulate the air and the HFO fluid. Obviously, heat transfer was obviously included in buoyancy, and we also accounted for all the heat losses to the environment and even to the ground. And yeah, just to get that extra to obviously simulate that specific scenario. Now, one thing, the big interest in this simulation was more the bulk flow rather than specific, pressure drop values and calculating that very accurately. Typically, when you're looking at values like that, like drag even over a car, you want a very fine mesh. But if you're looking at bulk flow, you can typically come away with a more coarser mesh, which is more than fine to capture that bulk characteristics. So in this case, we tried to limit the cell count to around 1 million cells. So we had to be very wise as where we're allocating all our cells to make sure we do at least capture the higher gradients with sufficient mesh count, and to make sure we're actually still producing a result that actually brings value. So in the end, we ran on 120 cores. Sometimes you might also realize, depending on the mesh count, the physics you're solving, scaling might sometimes also be a limitation. Like you can keep increasing the cores, but the amount of scaling you're getting is so decreasing that you're actually wasting money. So you must be wise sometimes in terms of how much cores you might use as well. But just to give you an indication, so this transit simulation took us 14 days in the CHPC to simulate 12 hours, right? If we did it locally at our own premises, it would have taken us 210 days. So I think that's almost like 7 months or something. So you can imagine our client's going to wait that long to get an answer. And I think, just looking at some of the results, I think I'll say it here. So this It's like you can see that there's the hot HFO coming out into the system. Obviously like hot air rises, hot oil will also rise, with everything else being much lower temperature. So we see it having this turning towards the surface. And I'm going to play this animation. It's going to show you in our increments of hours, like how actually the temperature distribution in this tank is developing. And just to note, I'm actually showing you all of the HFO in the system that's within this temperature range. So just recognize that. So, okay, just going to play quickly. So now we can see as it comes up, how it's distributing through the system over time. So everything, like I said, you're seeing now is at least within this temperature range, giving you an indication of that. So the next slide, I'm just doing a slightly bigger temperature range. Actually, not that much large. I mean, the previous one was like 31.5. This one is 30.25. But if we look at this one, we can get an idea of how actually quickly the heat is being dissipated and being distributed throughout the system. The client was very happy. I think what was actually wonderful is this was not necessarily the first the intended design. We actually had to make some adjustments to the simulation due to them. Actually, there was some slight miscommunication. But the wonderful news was we simulated this and they were so happy about it. And we actually gave them incremental results because 14 days is quite a long time. So we gave them results as we can every few days. And then they went forward with this design, actually just a normal pipe open at the end with the hot fluid coming into it. They were more happy with it. The initial design, sorry, I'll get to that one just now. Just some further value that I wanted to bring to my clients was they obviously did kind of their own calculations, with empirical values, or even using like walls as approximations to the tank to kind of just see what the temperature distribution would be inside the tank over time. And I could give them obviously a much more realistic value of like the air, because they actually thought that it would be like 25 degrees. And I could show them that it's actually more roughly around maybe 33 degrees. And in their case, it wasn't a problem. It was actually better. It was a good answer. But I could at least give them some more value than just like doing a simulation and get it done with. We really believe in whatever we can get out of the simulation for you, let's give it to you. Here you can just see that if you look at, this is the temperature of all of the HFO within the tank as it increases over time. So we can see, and that's the average temperature, we can see it started at 30 degrees and it almost ended up at 31 after 12 hours of being recirculated and reheated continuously. Okay, then I'm almost done with my presentation. So this is just the other scenario. So what we wanted to do is our client initially actually wanted to use a diffuser pipe with very small holes, 20 millimeters. So, you can realize why we had to talk to the clients, because they didn't actually initially communicate this to us. And we actually had to solve that transiently with find enough cells is a big killer, unfortunately. So we had to be smart about how to just still get value. And I think that's also what's wonderful about engineering, is that we are tasked with things. So like there is some limitations, but how are we still going to do something that we can get value of to walk forward to actually get answers? And that's what I also love just about being an engineer for myself. But specifically what we just did for the client is I thought like I didn't want them to walk away and have no idea if this would have been the idea maybe they should have went with or not. So I said, let's do at least a steady state simulation, just to get an idea maybe of kind of the flow patterns you can expect. And obviously the steady state, the final state solution of the temperature distribution, if you had this worst case scenario of temperature heat loss, just to give them, because they actually also did a steady state kind of analysis to kind of also predict what that temperature would be. So I can also provide that information to them as well. So in the end, what happened is the hot HFO came out of those very small holes, obviously were projected right up towards this free surface. And what was interesting, they had the idea of maybe it creating kind of a plume. And we're hoping for something like that. But looking at this, they realized that going this would have not actually provided the value they wanted, and they actually went with the first simulations approach and of building it. Just again, just so you can see the temperature range. So also the final temperature of the system was around 45 if we were to go to steady state. Okay, cool. I think just in conclusion, so thank you so much for that so far. So I would just wanted to say, keeping in mind what the title was of this CFD, of this presentation, saying new possibilities uncovering new possibilities in engineering with high performance computing. So keeping that in mind, I would just like to end off saying that we as Kosher Consult in our computer engineering department, we were able to, together with the CHPC, we were able to, with a very quick turnaround time, do very complex physics for clients. We did very large meshes as well, and a large number of simulations with the combination of that, which is really wonderful. And then lastly, we provided unique insight and value to our clients. So thank you very much.
Very, very interesting work. If I'm correct, you guys use OpenFOAM.
Yeah, so we predominantly use OpenFOAM for CFD at the moment. So if we do require, if OpenFOAM, for example, does not have the capabilities we do require to bring value to a client, then we would, for example, use commercial. I've myself have experience of 5 different CFD packages. So, yeah.
I think it speaks nicely to the theme of the conference that you're using open source software for this kind of direct engineering application. Very nice. Yeah. Do we have any questions from the audience?
I noticed you had a fire simulation, fire and smoke dispersion simulation that you showed there.
Yes. Yeah.
What software were you using for that?
No, sorry, just to correct, that was actually a data analysis, a data center analysis, not actually fire.
Okay.
Yeah, so sorry, just to correct that. I know, I can understand why it would look like it, but that was a data center analysis we did in-house to actually validate our approaches with experimental and published papers. So we go to great extents also just to refine in-house also all our approaches as well. But yeah, but I know you can do fire smoke simulations. I think OpenFOAM does have some capabilities as far as I know of it. There's also one I would look at as fire dynamic simulation, which also looks very promising. I'm actually interested in looking into ourselves as a company to do work for people. But yeah, but there's very powerful ones, and then obviously you get commercial ones. I'm probably sure like Starship Plus can do it as well. Fluent, I wouldn't be surprised if I would be surprised if they can't, because they're very big names out there.
Because we've had somebody do some fairly good work with FDS.
Yeah.
For the firework.
Yeah, I've heard many good compliments and comments about FDS. So yeah.
I'm just wondering, with the different fluids, how well established are some of the viscosities, and how important are they to the simulations?
Yeah, so I think you're also more now goodly specifically referring to maybe the last 2 projects, but yeah, that's a good question in terms of, especially if as far as possible, we always want as detailed information for any simulation regarding fluid properties. For interest sake, I think what might be interesting to me just to mention is that with the second project I was talking about was also a VOF simulation. There was, because it's a very unique, and they're also kind of designing towards it, they don't have all the information always. So sometimes we do use, let's say, at least representative values to kind of still make sure we can get quantitative and qualitative kind of values, or something you can just use with it, can give you a good indication of the direction which you're going to. Yeah, so that is very important. So actually looking at the clients with that second project that I presented now, they actually want to do even more work. So where we actually even investigate 4-way coupling within the particles, and because the simulation did show that there could be potential particle buildup. So they want to maybe investigate there, and they'll also want to actually look at heat transfer, because in that system the water is enters the system at 40 degrees, but the hot air, or so off gas, is 300 degrees Celsius, and the particles entering as well around the same temperature. So yeah, we want to look at the heat transfer actually with that particles into the water, if there's actually flashing even maybe happening potentially because of this hard particles hitting the water. So yeah, but I specifically wanted to mention about that is in that case for the heat transfer, having fluid temperature dependent properties is extremely important. Because I told them, because in the beginning they didn't have everything temperature dependent, and then I told them then it's not even useful to include heat transfer because it won't change the fluid properties, which will in essence affect the flow field, so it doesn't really help. So the first 2 simulations, the first work we did was more an isothermal approach, but in principle there was a lot of, let's say, good reasoning you can do to justify that it's more than sufficient for what we were looking at.
Yes, sometimes properties are available to predict from molecular dynamics, other material science.
Yeah, I must say that was very interesting to me today. I'm like, yes, you can do that. I actually want to talk to you about that, because I'm like, yes, because sometimes if you don't have anything just yet, you can actually use those tools. I was thought that's wonderful. So that was really cool thing for me to learn today. Thank you so much for that.
Other questions? No. I've got one last one for you, Charl.
Okay.
So just more on the parallelization and the the parallel efficiency of these these codes. I mean, we've got a lot of experience with OpenFOAM particularly. I mean, you mentioned you're doing quite a mixture of both steady state, so large scale steady state simulations, but also transient. And obviously one of the big problems we always run into is you cannot parallelize time. So you basically end up actually having to run quite small simulations for a very long time just because you can't actually.
No, exactly.
HPC is not actually helping you so much this. Have you got much experience with that sort of thing?
No, I think like from my most previous like experience, especially like because like just to give kind of a quick background, I studied at UP. I also did my master's there as well, but my master's entailed like CFD, FEM, and fatigue analysis. And I mean, from there, I kind of went on working in the industry mainly as a CFD consultant. But in that case, mostly we actually just used local machines to run the simulations. But I think the value that I've seen now with the business, with where I'm now, is that especially with OpenFOAM, I can actually give clients more value because OpenFOAM being open source, though very difficult to use, you must really know. I would say you must really know what you're doing. I wouldn't just let it's not like a commercial package that's nicely best practices implemented. You must really know what you're doing. But with OpenFOAM having no license cost, it enables us actually to give more to the client at a much better price. Because running the CSPC has no license costs associated with it, so I just pay basically the cost for running it, which is very, like I said, very affordable. And I think so. But working now recently a lot on the high performance computing, I've realized you should be careful because depending on the physics, the simulation, the mesh, and a lot of things, the scaling, you can't apply or the amount of, like, the optimal number of cores you should use to each simulation or each situation. So sometimes it's good just to run the simulation a few different configurations, kind of just see like, does it keep increasing in the same order that you're kind of increasing, as well. And if it doesn't, then for me, I don't want to waste my client's money and asking more money. I could give it to maybe 10 times faster or maybe 20% faster, but it's going to cost them additional 50%. So scaling is something I think you must take into account. To be honest,
Great. Okay. Thanks very much. Let's thank Charl one more time.